All right, so I'm going to go through these questions that you guys asked for the Big Idea 3 quizzes, and then just some general Big Idea 3 stuff that was unresolved. So the first question was asking about why I use a pipette instead of the burette. So for this question, notice it tells you you're using a volumetric flask, and then to make the solution, you're going to use a pipette or a burette. The answer, it could be either a pipette or a burette for your answer. It really doesn't matter. Normally when we're talking about the accuracy of a tool, a volumetric flask is going to be the most accurate, followed by, and we really haven't talked about volumetric pipette so much, I would consider a volumetric pipette and a burette about the same accuracy levels, just thinking about the lines and how fine they are compared to, like, for example, a graduated cylinder. So a graduated cylinder is going to be your least accurate, followed by a burette or a pipette, and then a volumetric flask would be the best tool possible. There's a question about your Beer's law equation in general. So remember, A is your absorbance, but then there's a question about what is your molar absorptivity really, and what's your B, your path length. And remember, C is your concentration of your solution. So molar absorptivity is actually a measure of how strongly a chemical species will absorb light based on whatever wavelength you set it to. And so that's a constant. It depends on that, the chemical that you're actually testing. Your path length is actually just the width of your cuvette. So the wider your cuvette, the larger your path length is. So your molar absorptivity is something you really can't change. And so there were questions on quizzes and tests talking about, okay, if I double the path length, what would have to happen in order to keep my absorbance the same? And a lot of people had said, like, double your molar absorptivity. You can't. Your molar absorptivity will always stay constant. Your path length you can change because you can just change the type of cuvette you put your solution into. And so you would have had to have changed your concentration to keep the same absorbance. Remember also that absorbance and concentration are directly related. The more concentrated your solution, your colorful solution, the higher your absorbance is going to be. So for quiz 3.1, the question was, how do we determine which reaction containing H2O2 we should use? And so this was for AI and AII that we had a question about. So for here, keep in mind, you got to consider what your reactants are. So there's a reaction between Cr2O7, 2-, and H2O2. So this Cr2O2, your dichromate, has to be a reactant. So this is going to be your reduction half reaction, which means peroxide, hydrogen peroxide, has to be your oxidation. So for this, for I, H2O2 actually you have to flip it, because remember, you always have to have a reduction half reaction and an oxidation half reaction. And so that's why it would be 133 plus negative 0.70, because you had to flip this to make this the oxidation while this remained reduction, since this is a required reactant. For II, notice cobalt 2 plus is a reactant, and you're going to react it with H2O2. So in that case, cobalt 2 plus, which right now is a product for your reduction half reaction, we've got to flip this over and make it a reactant. So this reaction here is going to be your oxidation half reaction, which then means hydrogen peroxide is actually going to be your reduction half reaction. So that's how I figured out which H2O2s to use, keeping in mind you always have to have a reduction half reaction and an oxidation half reaction. All right, for quiz 3.2, it says for part B, instead of saying SN atoms become SN2 plus in solution, can we also say that the electrons from the SN atoms flow through the cell to power it, meaning it's moving through the wire? Because keep in mind, for this reaction, SN is going to become SN2 plus, so the electrons are going to move to the left, I believe. Yes, because it's going to be oxidized. The answer is no, because it asks for B. As the mass of SN electron decreases, where does the mass go? So you need to keep in mind when you're looking at a galvanic cell or a voltaic cell, SN, if it is being oxidized, where does the SN go? Well, it becomes, and I always show this in my diagrams, an arrow going from the electrode, solid SN, it becomes SN2 plus. And so that's where the mass goes. It becomes tin ions, whereas the mass of the copper solid is going to increase. Where does that mass come from? It comes from the Cu2 plus ions that were in solution. So by saying that by talking about electrons, you're implying that the electrons have mass, which they don't. The reason why the mass decreases here and the mass increases on your copper side is because you are taking solid tin that has no charge and you're making it into Sm2+. That's where the mass goes. The electrons are transferred, but the electrons themselves do not have mass. Okay? How do cell potential and cell life, how long a galvanic cell runs, compare? All right, so the definition of cell potential, so the reason why, for example, here we have electrons moving from tin to the copper electrode is because there is a difference in potential energy between these half cells. I always like to think about a galvanic cell. When I introduced this at last semester, I talked about a waterfall. So at the top of whenever you see a waterfall, you know water is going to go from the top to the bottom because there's a difference in potential energy. Same with a galvanic cell or a voltaic cell. Your electrons will always move from the higher potential energy to the lower. The higher potential energy half cell is going to be your anode, where oxidation happens, because at your anode, for example, tin here, it's going to lose those electrons. Those electrons are going to travel from high potential energy, just like a waterfall, and it's going to go all the way down to low potential energy, to your copper. So a measure of that cell potential, which, by the way, I'll talk about this in a little bit, but that is measured in volts. So that is the voltage of your galvanic cell, right? Voltage is a measure of your cell potential. That is your cell potential. The cell life is how long that flow of electrons or that flow of water will actually last. Okay, so the faster your flow of water, the higher your cell potential is, right? Or the greater your voltage is, the shorter your cell life is going to be. Okay, so if you're shifting to the right, causing the cell potential to increase significantly, your cell life is going to be reduced. It makes sense. The more power your battery, the shorter its lifespan is going to be, despite what Duracell wants to tell you. Okay, so the greater the difference in potential energies, the greater your cell potential, the shorter your cell life ultimately. Okay, so that gets into the question that was asked. Is this non-standard cell powered for a shorter amount of time than the standard cell because the concentrations have been halved? So this has to do with this question right here. This is for D. So it says a non-standard cell is made by replacing the 1 molar with 0.5 molar. And the answer to your question, and so keep in mind, I am reducing the concentration of both of these solutions from 1 to 0.5 in this question. So by reducing the concentration of both of those solutions, yes, I am shortening the length, the cell life, because you have fewer reactants. Now, the reason why I want to reduce the concentration of both is if I reduce the concentration of just one of them, that would cause, for example, if I reduced the concentration of a reactant, what that would do is that would cause a shift to the left, and that would decrease my cell potential, which would require then more time for the cell to actually eventually die. So instead here, by saying, hey, I'm having both the reactants and the products, I'm not causing any sort of a shift. I'm just reducing how many ions are available to actually react and to accept electrons, and therefore I'm reducing the amount of time that this cell can actually run. What effects, if any, would an increase in only the concentration of the products have on the duration of a galvanic cell? So this gets into some convoluted stuff, because technically if you increase the concentration of your products, then you're going to shift the reaction to the left, which would decrease your cell potential. So technically, because you're decreasing the cell potential, I would assume it would take more time. The duration of the galvanic cell would increase. That would be my assumption. I tried to look it up to get specific examples. I couldn't find any. The most common thing that's talked about is simply reducing the concentration of both of these solutions, not just one of them. But I would assume if you increase the concentration of your reactants, since your cell potential increases because you're shifting to the right, that your cell would be powered for less time, while if you increase the concentration of your products, then your cell would be powered for more time because the cell potential would decrease because you're shifting it to the left. But that gets beyond any question that I've ever seen on the AP. What happens in a voltaic cell if a salt bridge is not present and the charges aren't kept balanced? So if the charges aren't kept balanced, the difference in potential energies, right, that waterfall is destroyed, basically. So you need to maintain that difference in charge in order to have that difference in potential energy. So if you don't have a salt bridge to maintain the charges of the solutions, then your cell potential will go to 0. Okay, and your cell will not be able to run because you're not going to have a difference in those potential energies, meaning you're not going to have a flow of electrons from high potential energy to low potential energy. Okay, for EI here, how would you know to use the 4th half reaction rather than the 3rd? So for this question, it says, using the information from the table above, write a net ionic equation. So we're reacting the tin electrode, so it's got to be solid tin, with copper ions, copper 2+. So your 2 reactants, and this is an issue that keeps coming up over and over again. How do you know what your reactants are? Read the question carefully. Tin is a solid here, so I have to use this 4th reaction, but I have to flip it, because this is the only reaction where tin is a solid. The 3rd reaction, doesn't have tin as a solid, so I can't use it. And then copper 2+ has to be a reactant. So I'm going to use the 4th and the 2nd reactions, and I'm going to flip tin, so it's being oxidized. Okay, question from 3.3, so number 2, please explain it. So for here, I'm given my cell potentials, and so I know that the only way that I'm going to get a thermodynamically favorable reaction or a cell potential that's positive is if I take chromium and I flip it, because that would give me a positive 0.41 volts for my cell potential. So chromium, if it reacts with Pb2+, it will actually have a reaction occur. Otherwise, Pb, if you have solid Pb reacting with Cr3+, right, if I flip this guy, you're going to get a negative cell potential. For C, you can't react chromium with chromium 3+, because the cell potential would be 0, right? Because I'd add this plus the negative of that. Same thing with lead. I'd add this plus the negative of it, and it would give me 0. All right, some just general questions. For number 1, in the response, you had said that a solid, so this goes back to the review questions from before. A solid and a pure liquid will not affect equilibrium. What is meant by a pure liquid? By pure liquid, I mean like if I gave you methanol as a liquid, right? Not water, normally for water, because for water, we're focusing on the fact that it's actually diluting, which is going to cause it to shift to the side with more ions. Why does it not have any effect? It just doesn't. So if you think about a solution that is saturated, it's in equilibrium, right? So if I have calcium carbonate that's saturated in solution, if you add more calcium carbonate, what's going to happen? You're going to have more solid at the bottom. It's just going to become a solid at the bottom. It's not going to dissolve more. So adding a pure solid or a pure liquid, it doesn't cause any sort of a shift. We see those shifts when we are adding aqueous or gases or water, because we're diluting. Why does access into the d orbital mean an element can be colorful and will absorb light? All right, so whenever you have transition metals, a lot of your transition metals are actually going to be colorful when they form compounds, when they exist as compounds or they're dissolved in water. And the reason why is, and I'm going to get into a little bit more chemistry than you probably asked for, but the reason why transition metals, when they're by themselves, like if you think about chromium or manganese or iron, whatever, they're not super colorful, and that's because their d orbitals, when they're by themselves, are what we call degenerate, meaning they have the same amount of energy. But when they start to bond with ligands or with any sort of anion, what actually happens is those orbitals, those d orbitals, become non-degenerate, meaning they have different energy levels. Now, that goes beyond the scope of the class because we're getting into molecular orbitals. But the reason why I'm telling you this is now their d orbitals have different energies. And so when those electrons move within the d orbital, they're now jumping different energy levels and releasing different energies. Those energy differences, when they're jumping in between those energy levels within the d orbital, those actually have the perfect amount of energy that it matches up with the visible light. And so that's why we can actually see it, because now that energy that's being released by those electrons moving around, that matches up with visible light. Okay? How are we supposed to know if a solution has color if we're not told so? you should be told so. Or, for example, if it's a transition metal, there's a good chance that it's going to be colorful. Not all of them, but a lot of them are colorful when they are dissolved in solution. Okay. For 3, we're going to be using this lovely Gibbs free energy formula with our cell potential. It says when calculating delta G with the cell potential, moles of electrons in R, what units should our answers be in? So I think what they were meaning to say was the F and the E. So for this formula here specifically, this is moles of electrons. So this was another question that was asked. This is moles of electrons, and I'll get into that in a second, how to determine that. Faraday's constant, and then you have your cell potential. So if you actually look at your cheat sheet, if you look at Faraday's constant, so I'm going to open up my cheat sheet. Okay. If you look at Faraday's constant and your cell potential, Faraday's constant is in coulombs per mole of electron, okay? And then a volt, which would be your measure for your cell potential, is going to be in joules per coulomb. And so your delta G that you measure is actually going to be in joules because the coulombs cancel out, and you're going to be left in joules for delta G. The other formula that I didn't put here, if you can add to your notes, please, your delta G equals negative, your delta G equals negative RT ln K. For that one, I think that's what you were referring to here. Notice your R value. If you look at your cheat sheet, your R is 8.314 joules per mole Kelvin. So that means your delta G is going to be in joules as well. So be careful because a lot of you guys mess it up on your quiz or your test by putting delta G in kilojoules when it should have been in joules. Okay. For B, N represents your number of moles. Yes, how do you determine this? So let me show you these 2 examples. So the oxidation number for iron here is going to be 3+. This is going to be -1, +2, and 0. So if you think about it, overall, this is a 6+ charge for iron. So it goes from 6+ to 4+, while iodide overall goes from -2 to 0. So +6 to +4, 2 electrons are being transferred, right? And then 2 electrons are being lost here, and 2 are being gained for iron. So your N for that would be 2. For here, you've got overall, so 2+ for oxidation number, but 4+ overall, 8+ here. Oxygen here goes from 0 to -4 overall because it's -2. And H+ goes from +4 and then, well, +4 there. So really what I would look at would be the oxygen. So oxygen here goes from an oxidation number of 0 to -2, but there are 2 of them, so -4. So for here, they're going to be 4 electrons that are being transferred. You can also look at it here. You've got +4 and +8. So 4 electrons are being transferred. So your N there would be 4. Okay. For number 4, in a potential energy versus internuclear distance curve, what does the dotted line signify? I don't know what you were referring to for the dotted line. Sorry. But I can quickly explain this. So if you're showing the distance between 2 atoms, here at the very top, when you have a really high potential energy, it's because the nuclei of the hydrogen atoms are too close together. They're repelling each other because your bond length, the distance between your atoms, is too close. So that's much too high of a potential energy. Then as they get further and further apart, you get to this very nice sweet spot here where you've got the nucleus attracted to the electrons just perfectly. And so that's actually going to be the distance between your nuclei. If they keep getting further and further and further and further apart, you're going to get to the point where you have potential energy of 0. They're too far away from each other. There's no attractive or repulsive forces. So I'm not sure which dotted line you were referring to, but there you go. Throughout electrolysis, does that same mentality apply that the reactions used, if not told, should be dependent on the highest, most positive cell potential, like in galvanic cells? Yes. So even though ultimately for electrolysis your cell potential is going to be negative, you're still searching for the most positive cell potential possible. And I'll show you that example in a second. For 6, what is the overall effect of gases acting non-ideally? Okay, so basically what we're asking here is, okay, if they actually take a volume, right, we had said that causes the pressure to be higher than what we would expect. Right? Because we had assumed they don't take up volume, but they actually do. So that causes the pressure to be too high. We assume that they don't have any attractions, but they actually do. And so as a result, the pressure is going to be lower than it should be. So basically what this question is saying is if both of these are true, how can you tell which one's more important? And the answer is you're not going to be. You're going to be asked one or the other. You're not going to be asked to compare which one has a greater effect. You're just not. Okay, so some practice problems for determining idealness. So if I asked you which gas acts more ideally, NH3 or H2S, remember the stronger the IMF, the less ideally a gas is going to act because we assume that there is no attractive force at all. So NH3 has hydrogen bonding in addition to dipole-dipole and LDF, while H2S only has dipole-dipole and LDF. So NH3 has stronger intermolecular forces, so it's going to act less ideally. Difference between F2 and Cl2, keep in mind they both have LDF, and so as a result, Cl2, because it has more electrons, is going to be more polarizable, so its intermolecular forces are going to be stronger, so it's going to act less ideally. Okay? Why do free-flowing ions mean increased conductivity? So when we talked about ionic compounds, we said that they can only conduct electricity when they are liquid or aqueous, and that's because they have their ions are free to move. That's because electrical current is actually transported through these ions. So another type of question you might see is, for example, which solution is going to conduct electricity the best? And it'll give you like 2 different ionic compounds or even 3 different compounds. So it could give you like NaCl, it could give you Na3PO4, and it could give you, let's say, for example, HCl. So NaCl only produces 2 ions when they dissolve, while Na3PO4 produces 4 ions, 3 sodium ions and 1 phosphate ion. And so that one's going to conduct electricity more because it has more ions, so the electric current can actually flow better. If it asks another molecular compound, I'm going to change it from HCl. Let's say, for example, I gave you NH3, for example. That won't dissolve in water at all. It's not going to break up into ions, and so that won't help increase conductivity. There's a question about doping. So you've got N-type doping and P-type doping. For N-type doping, you're adding an atom that actually has 1 more electron than the normal semiconductor does. So the whole point of doping is to increase the ability of that element to conduct electricity. So N-type doping, by having an element that has 1 more electron, you now have an extra free electron that can move around and can conduct electricity. For P-type doping, you're adding an element that has 1 fewer, so it creates a hole. So now it can actually accept electrons and help to promote the conducting of electricity. Okay, so the whole point of doping, again, is to increase the conductivity of an atom. What's the difference between calibrating the spectrophotometer and setting the wavelength? There's really no difference. So calibrating a spectrophotometer, you literally push a button and say calibrate. It's like zeroing a scale. When it says when you're setting the wavelength, you set the wavelength to maximize the absorbance. Remember, you want it 1 or below, but that actually gives you the most accurate absorbance reading when you set a wavelength to maximize the amount of absorbance up until 1. So you set the wavelength, you calibrate it, meaning you basically set it, you have a machine calibrate itself. So there's really no difference. I mean, they're different processes, but you're doing it at the very beginning before you can actually use the machine. For 11, why in electrolysis does the compound become, why does the compound being electrolyzed not even need to be present in the full reaction? So, for example, for NaI, when you show the electrolysis for this, keep in mind your reactants are going to be I-, water, Na+, and H2O. So your possible oxidation reactions are these 2. Your possible reduction reactions are these 2. So notice you didn't even need Na+, in order for this electrolysis reaction to occur. The answer is the reaction that's going to occur is the one that is most thermodynamically favorable, the one that has the most positive cell potential, just like that question that was asked before. So I- has the most positive cell potential here, and then H2O has the most positive cell potential here. Na+, I guess the question is, why is Na+ there? Well, to have I-, you need to have a cation that's attached to that anion. So for this one, it was Na+. It could have been Li+, but then Li+ might have actually contributed in the reaction. So the whole point is to get the most positive cell potential, but Na+ is there simply because you needed NaI. I- doesn't exist by itself. Okay? Why, when a reaction shifts to the right, does cell potential increase? I feel like we've kind of addressed this at this point, right? The reaction is by proceeding to the products, Your K is going to be, if your products are favored, meaning your reaction goes to completion, K is going to be greater than 1, delta G is going to be negative, and your cell potential is going to be even more positive ultimately. And so if you're shifting right, products are going to be favored, your cell potential is going to increase compared to if it weren't shifting right. The other way I like to think about it is it's kind of like something pushing that waterfall forward, right? So your cell potential, the difference in potential energies is even greater. You're going to have more voltage, more flow of water, which will also lead to your battery dying out faster. 13, why do we need a specific wavelength for spectrophotometry? Remember, we want to maximize our absorbance, like I said before. And what's the difference between cell potential and voltage, and how do shifts affect these? Remember, voltage is simply a measure of cell potential. Okay. And the last thing, acceptable abbreviations. Any abbreviation is fine as long as you're clear and write out the word first. So if you want to write IMF for intermolecular forces, make sure in the problem you first write intermolecular forces, and then after that point you can write IMF. All right, so as long as it's clear and you've used the full word before you use the abbreviation, you're good to go. And that's it.